what we're gonna do today is now consider it from what Stuart raised at the end of the last session, which was now 2 weeks ago. So what we covered the last time, just to do a quick review, since it's been a couple of weeks, we really looked at this intersection between both the torus and the cylinder. We kind of investigated this plane. You'd call it kind of like the well, it's the flat part of the bagel when you slice the bagel, basically. But it's that plane down the equator of the torus. And then if we said, well, all of our C's are on top, if our C's are on top of the torus, because that's the nature of these circles, each of these circles, they all have a specific B, which is along the diameter from A. So they all have a specific B, and then along the top of each of these circles would be then all the possible C's. And if all the C's are on the top of the torus, then going straight down to the diameter between A and B gives us all the possible D's. But then in the case of what we've been doing, we've been expanding this out. We've been giving ourselves a greater degree of freedom of hypothesis, which is really how the mind works. I mean, if you get stuck, you can either panic, you can try to force an issue, or you can just start to say, what are we not considering? How do I expand the perspectives to be able to give myself a greater degree of freedom to play with to get out of the restrictions? And so in this case, if each of the C's are these various circles, then the D's come down. And so then we said, well, how do we bind the D's? Having all of the D's along this flat plane don't really give us a clear picture. At least it doesn't give us some specific set. We want to create some specific set of C's and D's, and yet we want to do it in such a way where we give ourselves something different than what we had simply with the circle, or as we described it. We pretty much, when we just took the circle and turned it into a sphere, it really didn't give us much. The symmetries were too clear. It was totally symmetric. So it was basically just a redundant set of circles. In this case, we're getting something different. We have a different set of B's in this case, and we're now getting a possible D. So we said, what if we project a circle along that plane? So we say, let's let all the D's be that specific set of this contained by that semicircle, where it's still going between A and B, and there's a unique C above every D. So in this case here, well, this will be easier, maybe this one here. This one's kind of dry. But you get for every D along that circle, which is now a D along the line from A to B, even though B can be 1, 0, 1, 2, 3, and so on. So it could be any one of those B's, but for any line from A to that green line, which is kind of the equatorial line of the torus, from A, there's some possible B. And then each of those lines is going to intersect that circle, giving us a specific D. So because now when we choose a B, we're now given a specific D. And every specific D has some particular point C. So for every process now, so what we've created now is the first part of our circle, what we would call that unit circle. We now have expanded so that we have A, B, C, and D for every possible D, meaning every possible D as a possible length, right? But D can be AD, the length AD could be as long as the diameter or as small as 0. But that's its boundary conditions, that we have every possible d along this circle. It goes from the diameter to 0. But now for each specific d, we now have a specific b and a specific c. So every single option we can choose from A, if we're standing at A, you can see all the different possibilities. All the different possibilities of triangles. You can now see them kind of arrayed out in front of you. And that gives us at least some visual sense of an expanded domain of operations. We've given ourselves, you might say, a different palette. So you might say an added view of perspective. We think of the question of perspective in physical art and painting, how challenging that was. It doesn't seem challenging today, but clearly it took some time before that became a very clear representation. It may have existed in earlier Greek times. There's evidence to point that it did. But the kind of discovery and conscious discovery by the Renaissance was something unique. Okay, so we then took it and said, okay, that gives us then this red line. The red line is then all of the possible C's, which is really an intersection. It's an intersection of the torus with a cylinder built off this circle of D. And the intersection of that torus with the cylinder has a unique point of intersection, which is that red line. And Maria had raised, good questions about, well, is the complexity of that arc, that red arc, that important? And ultimately, it's not. We know that it fulfills what I just said, that every point along there is a valid point C. For every point along that red line, there is an A, B, C, and D that totally conforms to the way Archytas has defined the problem using this unit circle. So it's taken that unit circle idea and it's kind of stretched it or expanded it from a higher principle. It's given us something different to work with. So now we have to go back and say, now, is this the way Archytas thought of the situation? And what Stuart raised at the end of the last session was, ironically, how we could have started. We could have gone in the opposite direction. But we'll go that direction now. And it's kind of a question of which voice did Bach compose first, the tenor or the alto? You don't know. And in some cases, they're both simultaneously there. As one unfolds, so does the other. So what do I mean? So what we're going to look at now is the other way of approaching how this might have unfolded in Archytas's mind. Because there's another distinct relationship. The nature of this intersection was principally built upon these specific relationships. We really started with the relationship of just A, B, and C. We started with that. And we said, how can we expand the relationships of A, B, and C to maybe give us a greater degree of freedom? Once we had that with the torus, which we didn't find with the sphere would be a literal way. You say, take a circle and expand it into 3 dimensions. Most people would start with the sphere. But yet that didn't give us anything different. In some sense, you get an idea of kind of Vernadsky's discussion, or Pierre Curie's investigation of symmetry, and dissymmetry, because it really was this, and why Vernadsky might have been provoked, because these symmetries, it's redundant. You're not getting an additional dimension. But with the torus, we did. But then once we had the torus laid out, which is really based on the ABC. We now expanded our B's to be the equatorial line. And then we had to determine what is the location of the C's in this kind of carved out space. And it would be the top of the torus. Well, if that's where the C's are, we then had to ask, where are the D's? And that's what I just reviewed. So the intersection of the torus and the cylinder were largely based upon those relationships, A, B, and C, and then the unique specific relationship of D. D both to C, that it's directly beneath C, and also that it's on the line from A to B. So then the question is, we haven't solved the problem, but we've at least defined that one of these points is the solution. Now, I can say that for the same reason that we could say before, one of these points, somewhere around here, is the solution. You can do that by that method of exhaustion. You can kind of approximately say it does exist on the circle. So the question for Archytas would be, is that sufficient? Have I really changed the dynamic? So then the question we have to ask is, how do we come to know that we've really changed the dynamic of the solution, or our way of thinking about this? And that goes back to the other relationship in this unit circle. Okay, I'm just gonna pause there for a second. Are there any questions or thoughts? No? Okay. All right, so then this is the other relationship in this dynamic is what? Who wants to define? What would Archytas, what's the next step? Or what's the other parallel investigation we now have to take up?
AE.
Okay, so AE is one aspect. What do you mean by AE? What about AE?
Well, somehow it's proportional to AB in such a way that actually we had I can't remember how we did this, but AE will be larger than 1 because it's more than the radius of the AB, right?
No, I mean, well, what we want, if we go back, is always useful. If we start out with our proportional relationships, can people see that? It's not too high, is it?
Oh, that's fine.
Okay, so these are our 4 relationships. We know that AB, we're assuming AB to be 2, that the radius of our circle is 1. So the question is, can we get AE to equal 1? That's the challenge, right? That's part of the problem. Now, when you did this method of exhaustion, and you draw that other circle around A, the same radius of 1, but around A, it shows you where E has to be. E is here, it needs to be over here. So there's some disparity. We haven't found the right C. If we had found the right C, then E would fall upon that dotted circle perfectly. Hence the nature of the method of exhaustion. You could just keep getting closer and closer. So AE has to equal 1. That's one of the challenges. Okay, but what's the other set of relationships that are going to determine how we investigate this? So as I said, the relationships that determined the first part was A, B, and C. We started with the full circle and just the circle, no internal relations. Just the 3 points line along the rim of the circle. And we said, how do we expand that? because of course that's our boundary. Then we said, okay, well, within that, there's a specific relationship of the point D that is replicable between those 3 points. And so we created this intersection. What's the other relationship that we're now looking at? What do we have to now consider? We have to figure out how AE equals 1. That's there. That's right. That's accurate. But there's something else that's going to govern our point of hypothesis. I'll give you a hint. It's somewhere in that circle.
ED, I'm just throwing it out.
Right. Okay. Yeah. So there's a relationship that it's maybe worthwhile to draw a set of circles. I'll just draw 3. These really aren't circles, but they'll suffice. Hopefully you can see it, what I'm doing. So here's E near its smallest distance, AE at its smallest distance. And then you can see it growing. As C moves to the right, E expands. And then as it keeps moving, you get a larger and larger AE. But what's the one constant relationship? The triangle is changing. It's very small here. AE is even smaller than DE is. Here, AE and DE are practically equal, but there's still a 90-degree angle, and then AE is now longer than DE. So the triangle is constantly changing. The relationships of those 3 points are constantly, the way they're functioning is, it's not a similar triangle. Right? It's not always the same triangle. But it is specifically always a 90-degree angle. So what defines something to always be 90 degrees? And yet would give us the opportunity to become, any hypotheses of what governs or binds? If you say 3 points are always a 90-degree angle, what might bound those 3 points in space?
A circle.
Yeah, that's it.
Okay, a circle. Right. Something like that, right? Where instead of having ABC, we have ADE. Is that what you meant?
Yeah.
Okay. The problem here is that the D's length is also changing. So that means that when we draw it this way, we can draw every possible triangle that they would represent. But AD,
So it's effectively a series of different sized circles.
Mike, I think it says
okay.
oops, I can't see your picture anymore, so I can't describe it. Somebody.
Which picture?
Oh, there you go. Okay.
Oh, just make sure to pin my video.
Yeah, right. I try to pin it, but when someone talks or breathes or whatever and they're unmuted.
What it means by pinning is go to the 3 dots in the upper right corner of my video shot. Click on those 3 dots and it'll give you an option to pin this video. And that way, no matter who speaks, you'll always see my shot.
Okay, I'll try and figure that out. So what I was going to say is it's going to be a right angle if well, I was going to say if the opposite line, that doesn't make a sense. Never mind. All right, it's not right.
Okay, yeah, it's good to kind of just think it through.
One of the thoughts I had was that you know that E is perpendicular to AC, and that it has to hit the line AB at D. Well, obviously, because it's ED.
In video.
I don't know where I'm going with that, but that's I thought that somehow would be the key to finding where D must be. I guess not.
Okay, yeah, it's good that people are thinking this through. I like to hear the thoughts.
Can you hear me?
Yeah,
Okay, I was just thinking, it seems like what you're dealing with here then is like a series of different sized circles defined by AED. We're
Right.
defining a different set of AEDs.
okay,
If the lengths are changing, but the relationship defined by that right angle enforces it as a circle, then you're looking at a series of different sized circles.
right, okay. So how would we represent that? What are ways of representing different size circles?
A cone.
Yeah.
Right, a column. Okay. What other ways? Right, so whoever, I mean, so we have this circle, and then that circle. Oh man, that might be more of an ellipse. That might be all ellipses, by the way. Sometimes you get whiteboard perspective. But yeah, so a cone would give us multiple different size circles. What else would? Is the cone the only object?
You could do a horn
We could do a horn, that's right.
or a series of concentric circles also does it, but I don't think that gives you the transparency you need.
Right. Okay, so there's the horn, which is a similar idea of a cone, but it's still something different. What's another way of doing it? We haven't exhausted the possibilities of a 3-dimensional shape that has every possible size circle, or
A sphere
A
object.
sphere.
a sphere, right?
A pseudosphere.
Well, that's basically a pseudosphere. So you have the convex, you have the negative curvature, you have flat space, negatively curvature, and then you have where all these lines, or all these circles, all of these would become circles as well. So now we've defined the 3 possibilities that will give us the ability to look at multiple different circles of different sizes that capture this relationship, because as this is what Kevin's noticing, we've got, if you subtend that triangle, you've got a circle here, you've got a circle here, and then you've got a circle there. So the circles are actually growing. As C moves from A to B, as it moves clockwise around the top of our circle, the way we've drawn it, moving in this direction, the circle of AED is going from very small to very large. And so there's 3 possible surfaces which would give us some expression of that as a characteristic. So what do we think? So what do people think would be the next step? Do people have any ideas?
I'm thinking that the easiest to work with is the cone, because the sphere, you have 2 options then of the different size circles, both the northern and the southern hemisphere. and the horn gets kind of complicated.
Okay, yeah, so the horn is definitely complicated. The sphere gives us, and I mean, the cone gives us an idea, and of course, we're all thinking cone right now. We're moving towards the cone somehow, because that's the third surface. And the cone gives us some options. So the question then is, now this is where I think you have the interplay. And I think that he probably, like Stuart asked, how do we know he didn't approach it around AE equals 1 and the AED relationship? I would say that there's a basis to say he started with the broader contour and set up the problem similar to what we did. And when you do this, and then you go back and you say, okay, now I've got to figure out the catch, which is to maintain two things. That AED has to be 90-degree angle so that our proportionality holds, right? If that angle is not 90 degrees, our proportionality breaks down. They're not similar triangles, and the proportionality that we have set up wouldn't work. Even if that was 1, if that's not a 90-degree angle, doesn't matter. So it both has to equal 1 and be a 90-degree angle. So he's considered, what's this relationship I'm looking at? What's this AED relationship? And we've laid out the three possibilities that capture the way this relationship is changing, both as a characteristic nature of a triangle, but always 90. That's the only shared characteristic. It's basically every possible 90-degree triangle. But it's also changing in its proportion, it's changing its size. But then now go back and consider, where are our D's? Because remember, the one thing we have in this, in AED, well, actually we have A and we have a D. So if we try to match this hypothesis, we try to take this consideration and yet map it to what we currently have. How do we set up the problem of solving the AED relationship? That's a hint. Anybody have a guess? We're talking about mapping this conception onto these various surfaces. But you have to remember, we have to somehow define it so that there's an A, a D, and an E. The D is changing its distance from A, but A is always fixed. And we already have a certain set of relationships between A and D.
Can you move E along the diameter AB and then erect a perpendicular out to D?
Say it again, Emma.
Move E along AB. Along
We
the
have
diameter.
to move D along AB. Did you say D or E? David or Edward?
Along the circle, right?
Oh, I see. You're saying up here. Okay, right. So you're
Yeah.
saying E would move along the diameter.
Yeah, if you move E along that diameter and then from E, draw a perpendicular such that it the arc D.
Remember this circle isn't enough. So what I'm asking, but it's good. What I'm asking is that this circle won't be enough to represent it. We're going to need one of these surfaces. But we already have a relationship that A to D, where D is along this circle and A is fixed. And yet we need to create an ability that, for example, what we're saying is that every length between A and D, we're going to be able to generate a circle around it.
Hey, Mike, I have an idea, and I actually haven't been through this before. So
Okay.
I'm thinking that since D has to move along AB, and we've defined now a new AB that's not a line, but is the semicircle in the plane of the cut of the torus, that arc, that if you move D along that, that moves E in a way that's out along the cut of the cylinder. I don't know if I'm making any sense. Along the cut that the cylinder makes in the torus. Because you're moving, as you move the D along that arc, then that defines the motion of E starting from A. I see something there. I'm just not being clear.
Okay, no, it's good. So why don't we do this? Let's set up, let's now take what I've just said, kind of what people are kind of maybe pointing to.
Mike,
Yeah?
I was going to say, if you use a cone and you put A at the very tip of the bottom of the cone
Okay.
as a point that doesn't move, and yeah, that's A, and
Okay.
B is along one of the sides of the cone, and as you create the circles going up, am I right? And D is on that line too, either side of the cone, AB, up to the top of the cone, right?
Okay.
Yeah, and D is going to be somewhere along there. And then as the circles go around, you're going to have E on the other side of the cone at some point that you want the particular E. That's
Right. Okay. I mean, you have a sense of it. What we're having to figure out now is how we map these various changing circles in a way that will also map onto this process. So what we should do is, we can actually just, and I would imagine Archytas could do this. He would say, okay, I know that these are the various kinds of relationships that I need. Let me just define the way I have it. So let's just take a possible set of point Ds the way we have it. All right, here are all of our Ds. And here's A. What am I going to do with each of those lines?
Draw
Make
perpendicular.
Aren't you going to draw a perpendicular up to the circle that's going overhead?
That's what I would, you mean like this?
Where the red line
If I
is?
draw perpendiculars from D upwards like this, I'll be going towards the C's.
Would you just swing it around from point A, maintaining the angle, I guess?
Well, we could. The question is the circle, what's the nature of the circle? So if we define AED as a 90-degree angle, and we're saying that the nature of a 90-degree angle, what subtends it, what binds it in space, is a circle that touches all 3 points, when 2 of the points are part of the diameter. So if I draw this circle around AED, the subtending circle, so that we have a circle similar to the circle around ABC. So Emma, do you want to change your hypothesis at all? You're in the right direction, but you need to change it a little bit.
Maybe say it again.
Say what your first hypothesis was.
Well, I was thinking that you would just swing each of those lengths, I guess, which wouldn't give you a regular cone, but each.
So we would take AD and we would swing it around like this.
No,
Around A.
around A, yes, but
That,
not
right?
like that. Not like that.
Not like that. Okay, what did you mean?
Oh, no, I guess it is like that. But
Okay,
no, it's not like that.
that's not the circle we want, is it?
No.
What's the circle that we want?
One that where A and E are also on the circumference.
Right, okay, so what's the nature of that circle?
It has a different center.
Yeah. And what defines that? Where AD is the diameter, right?
A would be the apex of it, right? Of the cone. Well,
let's
yeah,
just-
it's down there, but A,
Let's just construct this circle, but now do it over here on this line.
the cone goes like this. Big part
But
of-
you're all operating off of
Can
where
you just,
be careful.
can you drop
You're
D?
not gonna get there with a straight path. Yeah, go ahead, sorry.
Can you drop D onto the diameter AB to create a right angle? Making
Well, just think,
E?
hey, this is where it gets funny because you're kind of staring right at it.
Yeah.
It's definable. You don't need to do anything else. You've got all the parts you need.
Yeah.
But we're getting juked by maybe how obvious it is.
Yeah,
This
Mike.
is- Yeah,
Yeah, well, AE is 1. We want AE to be 1, so why don't we just create a sphere of radius 1?
well, we can do that. We can do that.
Okay.
But the question is, if this is the relationship we're looking at, AED is a 90-degree angle of changing size circles. So we've got to we're going to create some type of surface that allows us to map every single one of those circles effectively.
Oh, make a 90-degree cone.
We could try a 90-degree cone. So you're saying a 90-degree cone like this,
And that won't that won't intersect anything.
and I guess you could say E would be over here while D is over here or something.
Mhm.
But the 90-degree, that means E would be here. And then A wouldn't be fixed because E is always where the 90-degree is. So here, that's why instead of having to do it from how to take those 3 points and map them onto a surface, just actually build it up. Right, build it up. Here we have A, D, and B. We have A and D already. We have lines between A and D. If I have a line here, A and D, what do I want to do with that line to define every possible point E?
Mike, what if you took like created a series of circles based upon A as one end, the D's along arc AB as the other end, and you effectively build a circle at each one of those cuts that's perpendicular to the circle defined by AB and the arc with the D's on it. Does that make sense?
Well, I had just posed a question, so I'm not exactly sure what you were saying.
We want circles of length with the diameter of AD.
Well, we want
Different AD.
Yeah. Okay, right.
And I'm proposing that we've got the various different lengths of AD along the diagram in the bottom left there, where you have line AB, and then you have that that semicircle with the D's on it. And if you made a circle
Where did you get this? I don't understand.
perpendicular
that's here.
to that plane with A and D as the endpoints of the diameter.
Right. Yeah. So if this was AD, if this was our AD, what would I do with this line to locate where E might exist? There's some E. In this space, in that space, there's a some possible E. How would I limit the possible E's that exist if I have that line AD? What do people think?
Well, within line A, B, you would mark out 1.
No, not AB. I have AD.
No, I know, AD.
Okay, yeah.
AD as a length has
Right.
to be smaller, or larger rather, than a hypothetical E, which is a unit away. It's 1, right?
It's not always 1.
It's not always 1?
No, not at all. I mean, the E's are only 1. AE is only 1 at one point.
Well, that's what we're looking for.
Yeah, I know, but everybody wants to kind of get there a little bit more directly.
All right.
Then maybe it's so just instead of trying to find the solution, just consider the question I'm asking so we maybe get a sense of a method by which Archytas was able to construct this in a knowable way. So I'm just asking a very specific question. If this is my AD, if I was given AD, and someone asked me, as I'm asking you, show me where E will lie, where the E could possibly lie within this space of this whiteboard.
When you drop a perpendicular, from E, it's got to be perpendicular to AD all the time.
No,
Right?
no.
But we're not dropping a perpendicular in this case. We know that there's an intrinsic relationship that AED is always 90. So what does that tell us about what we should do with that line?
Would you draw an infinite number of circles from like small, starting at A, just draw circles and increasing size to D? It's a hard thing to explain.
No, but you're close, but that would be too much. It's still a little too general. You can make it even more specific.
Can't you just draw 1 circle with AD as the diameter where we've been?
Yes.
Oh, yeah. Okay.
Right? That once I draw that circle, I know E is somewhere on there for that length AD. So the relationship of AED is that it's those 3 points always lie on a circle. So if I am given a set of ADs, if I'm given a multiple set of ADs, which is what I've drawn here, right? I have a set of possible ADs. Well, then I know that the surface upon which those fall is going to basically be the total set of circles that are subtending those diameters. Look, and this is the trickiest part of this whole thing. We're at the crux of why this has remained seemingly out of reach, for why it doesn't often lock in. So if you feel like, what is he saying? Because we're not dealing with then a surface in the proof. We're dealing with something underlying. Something kind of like the undercurrent for how this proof actually works. What surface would this be? What surface do all of those circles lie upon? Like if I asked you, what I mean by that is, if I took these set of circles for my torus, and I said just a set of circles. if I said, just take a set of circles that are, I'm moving, I'm holding point A as my shoulder, and I'm creating a set of circles that move in this way. What's the surface of that process? Where B is moving along that green line, and A is fixed at my shoulder.
It's more like
What's
a-
that surface that those circles create? In that case, it would be the torus. Okay, so you're basically saying if I take a certain set of circles, but I make it continuous, that it creates a new surface, not just a set of circles. What surface do I get? I'm asking that question now for if I take every possible AD and I draw a circle around it. In this case, I've drawn a semicircle. But if I draw a circle around every possible AD, what surface am I constructing?
It seems like it's sort of a horn, because it curves like a conch shell, sort of.
Well, think about this. What happens when D gets to B? Always push something to the extreme to find out what more you're dealing with.
Yeah, that would be the same size circle as the equator circle.
It would be. It'd be the exact same circle as AB is on. So now if we take the skeletal structure of that, what are we starting to look at? What does that seem to be?
A sphere.
Yeah, it seems to be a sphere, doesn't it? People see it? People see how these set of circles would end up becoming a sphere?
Not really.
Because it's a little bit difficult to imagine because it doesn't quite look like AB is a pole.
Right. Well, here's the interesting thing, and this is where the mind gets kind of funny. But if you took, say, if you have an orange at home or something, you have a spherical ball or something. Is it not the case that if I slice that orange, and say it's perfectly spherical, if I slice it, no matter how I cut it, no matter how obtuse or acute or skewed or whatever extreme kind of cut you can make, as long as it's a straight cut, what shape am I going to get when I open that cut up on the orange? Is it sometimes going to be an ellipse and sometimes a circle?
No.
What is it going to be?
Always.
Circle.
It's always going to be a circle?
Yeah.
As long as your orange was spherical.
Say it again? Yeah.
As long as the orange is spherical, it's a circle.
Yeah. Now, is that the case with the cone? That no matter how I cut it, it's going to be spherical. I mean, circular.
No, it depends
No.
on the angle.
Yeah, clearly, right? So in this case, when we have our set of Ds, I mean, it's possible you could take, like what Emma just, when I said, is it clear to people that that becomes a sphere? In some cases, maybe, those set of circles, depending on how thorough your set is, but you could possibly say it depends on how far you go. Well, yeah, I mean, because those circles are not, you could possibly, well, here's the interesting question. Emma, is there any point on the cone that could remain fixed? And you could draw these lines and they would still be circles? You could make, if I picked a point on a sphere, like this point here, and I did these cuts, would those be circles?
No.
Or if I said this was A and this was B, let me do it down here. Oops. if I say this is A, and as people were talking, maybe this is D.
You only get circles if it's perpendicular to the axis of the cone.
Right. So the only shape that that could create, even though those circles might, it's hard to see it because it's, let me see if I can draw it a little better. A specific representation of this. Because I think it's important that.
Might that be a cone that goes, I mean, it goes around AB as an axis point? No, I guess this doesn't make sense. Don't get it.
So if you try to say, I'm going to take a series of cuts that are all having one, where all the cuts share one point specifically, and they're all going to be circles, then I'm pretty sure that even though it's not obvious that this has to be a sphere, if you take these three, if you take those three cuts, if you try to imagine it in your mind, it's not easy. I mean, I think it's when the principle of powers paper that Dennis Speed has referenced lately, the Seattle guys they took up the doubling of the cube, and they did all these kinds of questions of building the solids and building volumes. It was a fun exploratory campaign. I think it got a little bit wild, a little barefoot and wild. But it was fun to do. It's worth having to kind of consider the sphere and its characteristics. I think somewhat necessary to exhaust it. It'd be useful to cut an orange, to try to cut it in different ways, as obliquely or whatever as you could, to see if it's still a circle. But for Archytas, this would have been somewhat of an intuitive recognition that once I start to build those AED circles off of these AD lines, that the only way that the only surface those circles could map on, because A is fixed, it's not moving along the axis of the cone in some way. Or in this case, AB or AD, 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 AD. They have to be moving to maintain the circles. But for Archytas, this would be then a characteristic of a sphere. Okay, so I'm going to move on because I don't want to just keep trying to argue that it's a sphere. But are there any other questions? Because it'll probably become more clear why we need that sphere. Archytas would have, because it's not the point that it's not as if at this point you have to know that that's what you need. You just need to know that that's something we would want to play with. Why we're not tending towards the cone, and why we're going to tend towards a hypothesis of a sphere around the ADB circle. We're going to take this circle and we're going to put a sphere around it. So do people have any questions of why we're there and why that's a relevant hypothesis, or just any kind of confusion? Because you don't have to, it doesn't have to be you just have to see it as reasonable. Does anybody find it irrational? No?
It makes sense to me that those circular cuts that we put there form a sphere.
Okay, good. Yeah, like I said, you have to see that at least it could be a sphere. I can kind of see the argument to say, I'm not sure it has to be a sphere, but I could see the fact that it could be a sphere. And that's all I would really ask people to consider right now. Hold that suspension. Okay.
Yeah, the only reason why it's a little bit funny even is because it's like a little bit different than how we originally thought about using the sphere to get a whole bunch of circles, because the orientation of each circle is changing.
Yeah, right. And that's where the sphere becomes, why the sphere becomes so much more useful in this case. That no matter if you have a fixed point on the sphere, let's say the fixed point, A is the fixed point, no matter which point I take on the sphere, any point I take on that sphere as a line from A to that point, and I took a knife and sliced it, every single point, every single slice I make is going to give me a circle. So now the symmetry of the sphere becomes very valuable. But that's more of a commentary than it is something important or something necessary. Okay. So what's along the surface of our D's are back here. If our D's are along the back end of the equator of our sphere, what's on the surface of the sphere? What points are along the surface of the sphere? Like if I asked, if we took AB, if we took our unit circle and we rotated it around, so it's pivoted around A, and B is sweeping along that green line. If I asked what's along the surface of our torus, what would you say?
C.
C. Okay, so now if I take the surface of our sphere, and this is A, B, and this is D, what's along the surface of our sphere?
E.
E. Because any point D I choose, as we did up here, will basically create every possible circle. In this case, if we take D and we go upwards, we're only talking about 1/4 of the sphere. So in some cases, like we said with the torus before, you're really only dealing with 1/4 of the torus, right? We don't have the front end, and we don't really need the left end. So we've chopped off 3/4 of the torus. The same is true with the sphere, but in principle, if the D's go all around, and we can go up as well as down for D's, then along the entire sphere, the surface of the sphere would be every possible point E. What do people think of that? Does that make sense? Is that obvious?
Are you saying that the D's are the equator?
The D's are I'm saying the D's are the equator. We basically built the sphere off of this circle. The bottom of the cylinder, we built a sphere around that as the equator. Who can tell me why we've done it? In quick summary, why did we build a sphere around that circle? What was the premise by which we built the sphere?
Well, we were
Because
looking
the
for all the, good.
Just that the semicircle represented all the possible Ds. And then we built the sphere to represent the, wait a minute,
Because, right, so.
the E's, sorry, yes.
No, yeah, well, we needed an AED relationship that was
Right.
always 90 degrees, right?
Yes.
So
Sorry,
no matter-
I was going further back than you asked.
Yeah. So if I pick a point up here in the back, of our sphere, if I pick a point there, I can draw a line from A to E, and then I can draw a 90-degree angle to some point along the equator. And that would be true for every point on the sphere. It's a little abstract. Let's get a little wild here. We're making some pretty big claims.
So, Mike, when you're saying that, Michael, are you saying the equator of the circle AB or the equator of the sphere?
When I say the equator, I'm talking about that circle around the middle of our sphere.
Okay.
I'm talking about this circle. Because it's this circle, this equator, which is where our D's fall, where our Davids fall.
Right.
And AB is the diameter.
And AB is the diameter in this case. I mean, we really don't need B, but it's kind of B not, or I mean, it's there. It just kind of helps give reference.
B or not B?
To be or not to be, that's right. It's a spherical question.
But don't you need B to build the nested triangles that are going to give you your proportions?
Not right now, because all we're doing is we've done all of this building it specifically on the relationships of AED. One, in principle, what is the principal relationship of AED?
And AB is a variable size then.
Well, no, AB is constant, and AD is a variable size. So that AD is a variable size, the relationship of the 3 points is always 90 degrees. So in that principle, and then we said, well, we already have a certain AD relationship. D is already along a circle in relationship to A. So it makes sense to kind of map these questions, or to bring them together.
And tell me you're saying AD or AB.
Okay, I'll say it's, yeah. So I'll say David, alpha David, alpha delta. How's that? Alpha delta. There's no B. I guess that.
Bravo.
Oh, beta. I can say beta. I got beta, gamma. C will be gamma. So alpha, delta, beta, gamma, and epsilon. Okay, we're gonna go Greek since we're dealing with Archytas. So the alpha delta relationship is a specific one. A is one specific point on the circle, and delta is the entire back end of our circle. That's the relationship we set up between alpha and delta. Now the relationship of alpha, delta, and epsilon is, as we've said, it's always 90, and the relationship of alpha and delta is changing anywhere between 0 and 2. And so we started with the conceptions of what kind of shapes would provide us that kind of changing dynamic between alpha, delta, and epsilon. We considered the cones, the horns, and then a sphere. Of course, we could consider spheroids and, ellipsoids. Well, ellipsoids probably not. But then we considered, well, let's take this specific relationship that we've created of alpha delta. Because we've taken alpha delta out of the unit circle, we've already started to build something different. We've created a different relationship. And so if we maintain that relationship of alpha and delta along this circle, where now does epsilon fall? Well, epsilon now falls upon any one of the circles that subtends, that circles the diameter alpha delta. And so anywhere along that sphere that I can identify as a possible epsilon. And that epsilon will have a specific point alpha, which is fixed. And for any specific point epsilon, there will be some delta. That the alpha epsilon delta relationship will be 90 degrees. See what we did there? We found a way of creating a surface relationship of all possible epsilons, where in here we created all possible gammas, all possible C's, all possible gammas with the torus. And then we had to define where our deltas might be. In this case, we're saying, where are all of our epsilons? If these relationships exist the way they do, where are all the possible epsilons? Well, they're on a sphere. And if they're on a sphere, then we can always create an alpha epsilon delta relationship that is both changing in size, that alpha delta is going from 0 to the maximum distance of 2, and that alpha epsilon delta will always be a 90-degree angle. Why? Because no matter how you slice that sphere, no matter which line you choose, this one, that one, any line you choose, any slice you make, in this case, we're always slicing straight down. That's going to make it a little bit easier. I mean, it's kind of, we don't need to slice it in every possible way. It's just to make the point, you could. But if we were just slicing straight down each of those lines, every slice you get is going to be a circle. And so now we've got a process. So the question then is, I'll pose the question and then see if we need to go back at all, see if there's any unresolved ambiguity. We now want to choose a specific set of E's, right? Once we have all possible E's, now we come up and go, what other conditions, how do we want to restrict? We have a whole sphere of E's. How do we want to restrict that? So that's the question we're going to answer. But before we go to it, does anybody have any questions on what I just went through? None? Are we sure? People get it? Why we built this sphere? How we built the sphere? Why and how? Okay. So then, if everyone's clear, what are we going to do? How are we going to restrict? What subset of E's are we going to choose? How do we limit our E's? We've got this whole sphere of E's. We don't need a whole sphere of E's. What E's do we need? What E's do we want to solve this problem?
A's got to be 1.
Yeah, I think a couple people said it. What did people say?
1.
1? Is that what people are saying?
The ones that equal 1.
The ones that equal 1. What do people think? Thumbs up? Yeah? Okay. Oh, it's not even. So does anybody have an idea of how I can create a set of points E where AE equals 1?
Ooh,
Go.
Make another sphere the same size where the center's A instead between AB.
That's true. That's true, but I'm not going to construct it that way.
Okay.
But that basically is we could do it. There's another way of constructing it that'll make it easier for me to draw and for people to see.
I was just
Yeah, I
gonna
guess-
say, take half of the line AB, because
Uh-huh.
that would be 1. Your AB is 2, so you take your radius and you rotate it, but I don't know how.
Okay.
I guess it has to intersect your your sphere surface, so you rotate to intersect your sphere.
Okay, so we rotate it over here. That touches the sphere.
Okay,
Then what do we do?
don't know.
Either way. Just rotate it all around where it.
Yeah, rotate all around.
Oh, yeah, rotate it over. I think I know what you mean. Let me see if I can draw it here. Is that what you meant, Emma? Maria?
Yeah.
Yeah.
rotate it from A.
Yeah, exactly. So it's kind of like taking this radius, rotating it over to this point where it touches a possible D, and then rotating it around A along the sphere. And everywhere that's green, we know AE equals 1.
So Michael, the distance to AE is not along the sphere, the surface of the sphere, it's a cut into the sphere.
No, this green line is entirely along the surface of the sphere.
The radius from A, though, doesn't.
I'm sorry, but when you cut, when you went, I'm using my cursor, but of course you don't see it. When you cut to the point where you're reaching this circle that goes
here,
AB circle, no, down. Yeah, that.
The circle, yeah.
Yeah, either one.
Yeah.
It's a straight. It doesn't go straight. It doesn't go along the surface to reach A. You go a cut in to the circle.
No, yeah, that black line is the line we're drawing, but the end point of that line. So this radius is the end point is sweeping along the sphere. You're right to say that yes, this line is not along the sphere. It is a straight line cutting through the inside of the sphere.
And that distance is 1, right? Because it would be
That
a
distance is
distance
1,
on the surface.
but that green line is entirely along the surface of the sphere.
Right. Okay.
Okay, that's right. Yeah, that's right. What do people think?
The sweep of the line that's anchored at A is sweeping out a cone.
Yeah, it is, isn't it? People see the cone? Should I draw it bigger?
But it's not an infinite cone, it's a cone of fixed distance up to a fixed distance of 1 from A.
Yeah, right. But we have drawn a cone now.
Yes, it would be good to have it bigger.
Okay.
I neglected to ask earlier, but now I have to ask, where is C?
Aha! C is along the cylinder in the torus.
What's it doing there?
That's where it exists. That's its home.
I knew we were going to end up with a cone. 1 diameter.
There's the full cone. I don't know if that helps, Evelyn.
Yes, it does. Thank you.
I mean, there's two factors here. One is that you can see the cone, you can see how it's manifest, and then two, you can recall how we built it. Kind of saw that we took certain specific relationships and then the requirements of solving the problem, that AE has to equal 1. And from those dynamics, we were able to construct a certain surface. What do people think? Are there questions or thoughts or reflections?
Yeah, I'm just wondering if there's one single point of E around that green line, which would give you a right angle to D, or whether any one of them could do it.
Oh, yeah, for every, that's a good point. Yeah, so we should now flush it out. So if I move up along this green line, if I'm moving up from the back towards the top, if I choose a point here between A and D, then my D is going to fall around here. If I go up further, my D is going to end up out here, being 90-degree angles. Do people see that? Do people see that dynamic? So as E moves up along the green line, D is moving away from the green line towards B. Right? As E moves up, that distance between A and D is getting longer. When I reach the top up here, D is going to be all the way at B. So there's this kind of relationship by which if we take some specific point D along that green line, there's a corresponding motion. As E moves up, D moves. As E moves up, D moves around. Good question.
Kind of like the D on the torus.
Yeah, just like the deltas in this on our cylinder here. Just like we moved here. Now this is the funny part. As we move along B, as we move B along the equator of our torus, sorry, beta, we take beta along the equator of our torus, delta is moving this way as B moves around. So they're moving they move together, they move almost parallel. As B moves around the torus, D moves from B from beta towards alpha. If you're getting confused, just remind me to go back to the Greek, because I'll tend to forget.
Well,
yeah, go ahead.
The thing that has been puzzling me is that once you've identified the arc, the red arc, all you need is the radius of half of AB anchored at A, and to intersect C, the C's.
Yeah.
I guess you're calling them gammas. And that excuse me, that does construct the point. Now, the problem I've been having is that why would you look for a locus of all E's when you've already got the basis for constructing the exact point you need?
Well, I don't know if what you described is the basis for constructing the exact point. And I don't know if it resolves it in the mind that you maintain all the relationships, or you see how the surfaces came about. So I'm not sure what you said. And you might have it resolved in your mind, but what you just described, if we have the length A to some point is equal to 1, we know that. Yeah, that's true. But we also knew that in our basic unit circle. We have this point here. So the question is, not only does AE equal 1, but the point is that AE has to equal 1 when alpha epsilon delta is also a 90-degree angle. So that's been the catch. If you remember, we go back to how we defined that unit circle and how Archytas defined the problem. There was this kind of, you can either AE can be 1, or alpha epsilon can equal 1 as a distance, or alpha epsilon delta can be a 90-degree angle. Getting both of those to converge is theoretically possible, but to know the point C, to know the specific point C, where that relationship meets, that alpha epsilon is equal to 1 and alpha epsilon delta is 90 degrees. That we haven't known what point gamma, what point C, what point gamma actually resolves that. And so what we've done is we've constructed now a surface where alpha epsilon delta is always 1. Alpha epsilon delta is always 90. And now we've got a certain, which is the sphere, and then we've constructed a surface where alpha epsilon is always equal to 1. So we're really close to solving the problem. I've just got to wed the 3 surfaces. But I'm kind of letting just people sit in the tension. But so it may be resolved in your mind, but I don't know. But it doesn't. But we had to. I think these steps were necessary. To see how and why it resolves. But should we resolve it? Do people want me to just put it all together, or should we go there and then come back and see if there's questions?
Well, we could resolve it next week.
Yeah, we could. We could wait. You want to have like that part 2 next week? Hold the tension, all the suspense.
Hello, I have a question.
Yes.
Yeah.
Okay. When you finish the final session, the final class, will you build the cubes? One cube representing the unit on the altar that has to be doubled, and a second cube, which when you fill it up with water, will have double the volume. Let's say you pour water or your favorite coffee. It doesn't have to be.
I wasn't planning on building any cubes.
Answer in your last class. Will you demonstrate in physics after you finish your series of class? Will you? Yes or no?
I feel like it's a challenge. No, I wasn't planning on it.
I do. I know how to. If you want to talk to me, we can do that towards your last class or anytime you wish.
Okay, sounds good. Okay, so let's just consider where we are. Because what happens is you get into this and you have to imagine why we're doing certain things, and it's hard not to see this as kind of Bachian polyphony of developing different voices, but yet always having a similar principle in mind by which you're constructing these voices. And so we wanted to define a set of possible C's that was outside the circle, that would give us a new set of possible C's, and really would give it to us as an arc where each C, each point along that red line, gives us has some particular D, some particular delta, and some particular beta. And so if we know that for every gamma along that red line, for every C, for every gamma along that red line, it fits and corresponds to our unit circle. And so we have that. We have a certain set. And I often imagine standing as if I was at alpha and looking at this red arc, knowing that I've got this kind of this circle of D's around here, going from A to B. And I've got this red arc that curves up as well as back and then comes forward as well as down towards me. And now all we have to do is locate one point C, one specific point C, where AE equals 1, that alpha epsilon equals 1, and AED, alpha epsilon delta, is 90 degrees. If we can find one point along this red arc that intersects this cone, then we'll have solved the problem. Because our cone has, for every alpha delta relationship, for every alpha AED, alpha epsilon delta relationship, we know it's always a 90-degree angle. It's always 90 because it's always a circle. There's always a circle subtending those 3 points. And we know that along the cone, that not only is AED always 90, but that alpha epsilon is always equal to 1. So as long as the cone at some point touches that red line, and A is there, we will have found the location of that mysterious point, that elusive point C, or point gamma.
And Michael, is the AB lying on the other AB? That's also the way it's
Say
set.
it again?
The AB is lying on the other AB, right?
Yeah, I can
Yeah.
draw it out.
That's okay. I just want to make sure.
Yeah.
The whole cone doesn't define the A equals 1. It's just that green arc that was created by rotating the radius out, right?
This whole cone guarantees you alpha epsilon is equal to 1 and alpha epsilon delta is 90 degrees.
It's not just that one green arc that we originally used to define the cone.
Craig,
They're the same surfaces. It's just kind of extending the cone out further.
Very hard.
So it's essentially the same surface. The point is that if this is my AE, my alpha epsilon, I know that to reach my point gamma, to reach that point C that I want, I have to go beyond. I have to extend it somewhat further. How much further? I don't know. I know that if I go out to 2, if I extend this to be double, I know that'll be sufficient. I know AC, alpha gamma, cannot be longer than 2.
I see what you're saying now, yeah. That first green arc that we defined was the one that's defined by AE, but that defines the surface, and the C is beyond AE. It has to be longer. So it has to be along that surface we created.
Right.
That's it.
What do I want to erase? Yeah. Should I draw all 3 surfaces? What do people want to do? We've got about 20 minutes left if we want to use it, or do we want to cut and come back next week? Or should I draw all 3 surfaces?
Why don't you go through it once?
All right. Okay, there's all three surfaces. I don't know if you can see that or not. Here, this might help. So you have the red line, right? That's the cylinder, the back end of the cylinder. That's cutting into the torus. So the back end is similar to this blue line back here. The red line is where that cylinder cuts into the torus. We talked about like a small tomato paste can cutting into a top of a bagel. As an idea of that process, something you can do, you can construct it fairly easily to investigate it. And then we have the points, A. We have the B's going along the back end of the green line. We have our D's along the blue line. We have our E's along this green arc. So that's all three surfaces. Now I can draw a couple of other things. I can show how these relationships kind of work. I can even show where I think the point generally exists, where along the cone a pathway extends to intersect that red arc. I could show you where that approximately would be. But what do people think? Do people have questions? Is that confusing? Should I try to draw another representation? So what you want to have in mind is that we're sweeping along this cone. Okay? You want to put yourself at point A. Put yourself at A. At least this is how I imagine it. So you get off of the two-dimensional paper or whiteboard, and you put this in three-dimensional space. What have we actually shaped here? Let's take it off the blueprints and actually construct it. And put yourself in it like we would put ourselves in the nighttime sky, that starry dome. Well, if I was standing here at A, as I said, I went directly across me the length of my diameter, I would find B. If I swept back the depth, the length of my radius, I would have an arc of a circle, which is where all my D's are. If I go up a radius and back at the same time, so I go up and back and then down and forward back to B, I would have this red arc. So I can see the red arc basically here. At least maybe my imagination's a little too vivid, but I can see this red arc as it's constructed. And I know that one of those is the right C, is the C that will resolve the issue, the way Archytas defined the problem. But then I take this cone, I sweep out an arc, I go to the back end of my circle where the D's are, and I draw out that green arc of E's. So if my length of my arm was 1, which is, let's say it was the length of my radius, I can now imagine going back to the circle where the D's are and sweeping an arc out with my arm. That would create that green arc where AE always equals 1. And the relationship of AED is always 90. So now all I have to really imagine is if somewhere as I move my arm along that green arc, at some point, as this red arc goes backwards and then forwards, it goes back and up and then forward, down and forward. As it does that, I'm taking my arm and moving it along that green arc, and I'm extending my arm, twice as far, like a laser pointer or something, or like if I had a yardstick. And somewhere as I move my arm around that green arc along the sphere, that yardstick is going to run into that red arc. And you really just kind of have to, if you set it up in your mind so you can see the relationships, that has to happen. There's no way this cone can move from the back end of that circle here and move forward to the front end and not, as if it's extended outwards, not run into that red line. So what happens when it does? So as I move along the green cone, I reach a certain point where my yardstick would hit the red line. That red line would be dropped down to D. Well, that red line, that point, with a line from A to that point C to B, will be a 90-degree angle. It will fall within the circle that's along the top of the torus, some specific circle. So that angle ACB, or alpha, gamma, beta, would be 90 degrees. Alpha, beta would have a distance of 2. From alpha, gamma, from point C straight down, I would find a valid point delta that intersects that line AB, or alpha, beta, at 90 degrees. I can then go from delta to my point E, or epsilon. And that point E will be the point where if I draw a 90-degree angle from D to that line AC to be 90 degrees, it will find that green arc. It will find that green arc so that alpha epsilon delta is now 90 degrees. And because it's on that green arc, alpha epsilon will equal 1. And once alpha epsilon is 1, 90 degrees, 90-degree angle here, and a 90-degree angle here, then these relationships all hold, and the length AD would equal the cube root of 2.
And all those things are on one plane, right? Like our original unit circle.
Yes, they would. All of those would fit on a plane that, if you sliced it, it would AC would project straight down to AB.
Right.
If you took a slice of the torus, it would be one specific circle. Right. If you did a top-down slice of the torus, you'd get a circle, and that specific circle, all of those relationships would fall within it, just like they did within our unit circle.
And AC would equal the cube root of 3?
AC would equal the cube root of 4. And then AB equals the cube root of 8.
Yep.
Or 2.
Yep.
But you have to go through all this to find which unit circle out of the infinite unit circles defined by the torus is the one that has the relationships we want.
Yeah, right. When we limited that down to some set of possible gammas, and then we had to figure out how to define one of those gammas so that alpha epsilon equaled 1 and alpha epsilon delta was 90 degrees.
And then by doing all of this, that length alpha delta is the edge of the cube that is twice the size of the original one, which has the edge alpha epsilon.
Right. That's what we theoretically were able to prove, yeah, with the various idea of similar triangles. So the idea here was to make clear, one, that why this works, which we maybe there may be some foggy questions. Like, what I'm going to do with the group here is next Saturday, not this Saturday, I'm going to go through a review and see what people remember and what they forgot, what seems clear, what doesn't. But it's also a question of understanding how Archias came up with this hypothesis. Because it really is, and not to say that what we did was what he did, but at least it tries to capture how one can unfold and solve problems where you can get clear or distinct kinds of knowledge or understanding. So the important in my mind is that people recall, if you can recall anything, you want to recall, how do you generate the surfaces? Once you kind of have a sense, yeah, that works, that does do it, I see how we did it. The question is not simply that it does it, but can you recall the means by which we unfolded the various surfaces? Because that's what, in my mind, is the richness of the composition. So are there any other thoughts or questions?
Yeah, I tell you, I really enjoyed this whole process, and the question of the right angle at E is something that I had really overlooked, and it's been very interesting, very, very interesting. So thank you very much.
Yeah, sure.
I guess my question still is, how would you determine what the measurement of AD would be? You know, like you can determine what the diameter of a square is, 2. You can't. It's not a infinite number, but you can determine what it is. Can you determine what is there a specific way to determine, like with a compass, where that C would be and where the D would be?
No, no. I mean, you're defining the point in space by the intersection of three types of circular action generated from a certain given location A.
It seems like it's like doubling the square, except more complicated.
Well, that's one way of putting it, certainly.
But certainly incommensurable.
Yeah, certainly incommensurable, yeah. But it's like we said before, if you go back to the initial introduction of the course, it's why I said play with the notion of three-dimensional space. Because there's quite a difference when you're talking about three-dimensional space. The only time you actually interface three-dimensional space is when you introduce motion. And by introducing motion or movement, you're creating the characteristics of what you would say in reductionary terms is for the fourth dimension or 4 dimensions. So when you're dealing with the square and 2 dimensions, you still need ultimately to move, to create that kind of logarithmic motion from simply the side of the square to its diagonal. As much as there's a motion involved, you're still dealing with an artificial construct of space. But once you start to deal with motion in 3 dimensions, you're now dealing with a characteristic, you're less removed. You could say you're even just kind of infinitesimally removed from physical space. You're still an artificial construct. But you're far closer. You're almost tangentially close to physical space. And so the nature of getting something nice and neatly packaged, it would be less expected. And so I think none of the proofs will deal with a cube per se. I mean, as Eli mentioned, I mean, he's built some great models, and people in New Jersey and others can see what he's constructed to really go through this as a physical construction and build the altar, so to speak. But it certainly is more so not that this works. And Archytas wasn't simply looking for something to work. He wanted to demonstrate a quality of thinking that comes closer to understanding how do you pierce the veil of sense perceptions within physical reality. How do you come to know something with a degree of certainty? Far less than you will in geometry. Geometry is easy compared to physical reality. But at least it gives a basis for how to think about what it means to know something when you're dealing with chaotic times like a plague. Because there's no time in civilization when a plague has ever been anything but totally chaotic. Political instability, social instability, psychological breakdowns, the unrest of youth, because they're thinking about their whole life and all of a sudden there's ahead of them and now there's this massive plague. So there's always that instability. So how do you now get above the fray and think more clearly about how to know what's actually going on, or perhaps better, know how to think about solving the problem? So those are my reflections. Anyone else?
Yeah, it's Judy Clark here, Mike. And
Hi.
I'm glad you introduced the political, physical geometry that we're in, because, you know, the title of this thing that Dennis wants to do tomorrow is bring in Graham Lowry and Lynn on, you know, the future of this 4th of July concept. And it's that idea that he was also using, the discussion that you guys had on Thursday was, you know, you can only know what creativity is if you use it, you know. So what is the republic? What is it to be a citizen? How do we wield any of the knowledge that we think we know until we apply it. And so it's just very refreshing to see all of my friends and colleagues from all these decades delighting in the mind of Archytas. And, you know, I appreciate that you brought this forth for us at this time. It's very rewarding.
Good. Okay, so any other thoughts or reflections, or what people would like, if people want to do another week of review or let it sit? People can send me an email on that question if you don't want to answer now, you want to think about it. Any other thoughts or reflections or questions?
I can say it's the first time that this has kind of been clear to me, but that brings me to the answer to your question. I think we should do a week of review to see how much actually stays or how many questions come up afterwards.
I agree.
Okay.
Yeah, I agree.
Okay, good. We'll do one more week then. Kevin, when you said that it's somewhat clear, is there something that stands out to you that's not?
No, but it wasn't clear at all before. It was opaque. We've achieved at least translucence.
Good. All right.
I still got to go out of the room and make sure it comes with me.
Right. Yeah, that's always the big step. Yeah.
Yeah.
It seems clear now, and then, you know, a couple of days later, you're like, that's why the important part is to try to recall the generation of the surfaces. Because if you can in your mind demonstrate the necessity that the cone will have to intersect that red arc, the arc generated by the intersection of the torus and the cylinder. If in your mind that's clear, then the question is, so then you know that it's possible to get to this end point, that we can generate a specific point C where all these relationships hold. Well, then the question is, why did we generate each of those surfaces? Because if you don't know why you generated those surfaces, if you don't have some means of recognizing what they provided, why we considered that, then I think the method of thought is what we're fighting for clarity on. Not just to know that it works, but how we got there. Okay, anything else? Any Archimedean exaltations? Eurekas?
Thank God it's over. Now we can put the air conditioning back on.
Okay, that's good. Getting a little hot and bothered, huh? Okay, good. Well, then let's call it a wrap for today. And if people have questions, maybe it'll be helpful for the review if people could just send me one question or thought about what seems to be unclear. So if you try to rethink it, redraw it, reconstruct it in your mind, and you come up with something that you get stuck on, send me a note on that. It'll help a lot to know what specific points I need to make in a review. That'll make it more productive. All right, glad people could join. It's been fun.
Thank you.
We'll do one more week. See you next week.
Thanks, Mike.
Yep, bye.